Working with the trigonometry for our visual movement requires us to use a couple of different formulas. And these formulas allow us to, instead of having to figure out movement where we have to say, okay, I have a speed x and then I have a speed y and that's how I'm moving. Instead, we're just going to say, I have a speed. And the speed will be on our triangle, the hypotenuse, the diagonal line, and the angle that we're moving. So we just keep track of what is that angle. So this red triangle, where the dot represents the player as it would be trying to move, on this red triangle, we have three sides to the triangle. So we have the vertical side of the triangle, we have the horizontal side, and then we have the diagonal. Now, in this example, the diagonal is of a fixed length. So the hypotenuse is set at a length of 200. And I did that just because then it gave a big enough circle on screen that we could see. Now, when we are going to be moving on screen, to move from the center of this circle to the red dot, it requires me to then move that dot the length of my adjacent side, which in this case would be 139.92 pixels, and to move along the opposite side, or the vertical part of the triangle, 142.9 pixels up. Well, when we're moving up on screen, that's a negative number. If we're moving down on screen, it's a positive number. If we're moving to the left, our x movement along that x-axis is a negative number. If we're moving to the right along the x-axis is a positive number. That movement on the x-axis is going to be our adjacent movement. And the movement, so the adjacent, the horizontal, the movement on the y-axis is going to be our opposite, or the vertical. Now, there's a really couple simple of trigonometry formulas where if we take the sine of the angle in which we're moving, then that is going to be equal to taking this opposite, dividing it by the hypotenuse. So if we know the angle that we're moving, if we know the hypotenuse, or our speed, we can then simply figure out opposite, which is going to be the sine of our angle divided by our hypotenuse is going to give us that opposite, or multiplied by the hypotenuse will give us that opposite side. So we could rewrite these formulas, so instead of being the sine of the angle is equal to opposite over hypotenuse, our opposite side is equal to the sine of the angle times the hypotenuse. But the way that these three formulas are commonly referred to is it's SOHCAHTOA. So that's those three triplet letter groups up top is SOHCAHTOA: sine over hypotenuse, cosine, sine opposite hypotenuse, cosine adjacent hypotenuse, and then tangent opposite adjacent. So these are the three ratios where if we take a sine of an angle, a cosine of an angle, or a tangent of an angle, we can figure out the different sides of a triangle. And it's this triangle magic that allows us to calculate movement along an angular vector. And that's where it gets really, really, really fun. But when we look at this, we can just take hypotenuse, bring it to the side over here. So our opposite, the vertical part, would be the sine of our angle times our speed. And that's how much we have to move in the vertical dimension to go from point A to point B. And then the cosine of an angle times the hypotenuse, or our speed, will give us that adjacent side, or how long we move along the x-axis, or our horizontal axis. So those values are going to make it super easy for us to then figure out how to get our player to move along an angle when we say the player is rotated to a specific direction. Once the player is rotated, we know we will assign it a speed. So that means we know an angle, we know a speed, and if we know angle and speed, we can figure out the other two angles, or the other two sides of the triangle. To work with this, what we are going to need to do is we will need a couple new variables that we can work with. And we're not going to need speed x and speed y anymore. My advice as we're modifying this is to comment out what we were using, and then we add in new stuff. So I'll say float, and then I will just have a simple speed, rotation, and eventually we're going to want to max speed if we want to allow him to be able to accelerate and then decelerate back down, because I think that's more fun than I push go and I'm at full speed. I let go of go and I come to a dead stop. That's just not as satisfying as a play experience. So we're not going to program max speed right away, but we will work towards it. So speed, rotation, and max speed. Now these speed x and y is going to eliminate those. And now speed will start out with a value of 0. Rotation will start out with a value of 0. And max speed will start out with a value of, and this is where max speed is how fast do we want it to be able to go? 5, 10. I'm going to say 10 so we have something to accelerate towards. Now, as you start working on your project, what you may find is that, well, 10's too fast or too slow for your given artwork. So then you modify that maximum speed limit for your player. But 10 tends to be a decent speed that we can work with to make this happen. Now, currently, if I push the left key, he moved to the left. But instead, I want to rotate left when I push the left key, and I want to rotate right when I push the right key. So I'm going to comment those out because I know I don't need those. So when I push left, instead what I want to do is I want to take my rotation, and I'm going to subtract from it 5 degrees. But if you remember, I mentioned we do need to try to use our values in radians, not in degrees. So if I want to subtract 5 degrees, but my rotation value needs to be in radians, processing has a really cool function built in, where I can just say radians, and I'll just say 5, like that. So that now subtracts 5 degrees, but it converts it to radians. That's what the radians is doing. And now that we have it rotating that way, we can see that I can do a rotate plus equals when I turn to the right, because that's now adding a positive value to my rotation. So far, not so bad. Now, right now, we're not going to even worry about if I am pressing both buttons. We're not pressing any buttons how we want it to work. So we're just comment that out. And once again, when we are modifying an existing code that was working, it's a really good practice to not delete. Just comment it out while you're going, because you may want to look back and go, oh yeah, that's how I did it, without having to reopen an old file and stuff like that. So comment things out as you're going. You can always delete old commented code out once you have it ship shape. But I like to leave it there until it gets to be too unwieldy and just too much stuff. Now, when I press the up key, currently it does speed Y, press down it does speed Y. Well, we're not going to use those anymore. If I press the up key, what I'm going to do is say speed is equal to, right now I'm just going to just hard code it to 5 when I press up. Now if I press the down key, I'll set my speed equal to 0. Now if I don't make it possible to set my speed to 0, well then I could run into problems on it. later. So if I don't have a way to slow back down, because I don't have friction, I don't have deceleration built into it right now, I need some way to slow it back down. So it would be nice to build that into it. Now, we're not going to worry about these right now. We will come back to that in a little bit. Now, finally, what we're going to need to add into our project is we're not going to modify x and y by speed x and speed y, because we're not using those anymore, so we need to do something different. So it will be x plus equals, and now this is where we have to do that little bit of pesky trigonometry. But the two formulas is, if we remember, x is moving along our horizontal value, and that used cosine as part of it. So we'll just say cosine, and then I'll type in rotation, and then we multiply that by our speed. And y is going to be the same thing, but with a sine value. Rotation is the angle that we have rotated the player to, and we are going to make it move based on speed. Now, if you're getting antsy or you've possibly already done it, you can always try and run the code and see what happens. Now we can see I went off screen. I have no wrapping, so I immediately lost where I was. Now, because the player isn't visually rotating on screen, it's making it really hard to figure out where is the player? What is actually happening? And this is where we need to go back and use some of our matrix and translate and then actually rotate the graphic for the player, much like we did with the planets in our solar system a couple weeks ago. So it's moving right now. If I hit run and go forward, we can see, okay, it runs, and oh, look, so it's going. But if I'm not rotating on screen, it's kind of hard to figure out what direction am I even going at this point. I don't know. And we may want to then put in some screen wrapping, either put in boundaries so we can't go off screen, or we need to put in screen wrapping that allows us to wrap the screen asteroid style, which is what we will add to it in a little bit. But first we'll get the player rotating and working with that. So just not really going to be using those lines too much anymore. What we need to do is we need to push our matrix. And before I put anything else in, I like to pop the matrix. So I know that's like doing curly braces. Always, every time you do an open curly brace, always do your closing curly brace, then put the stuff in between. Because otherwise it's so easy to forget to close it. And then you're like, why is my code breaking? And now inside that matrix, it doesn't require an indent, but I view push and pop matrix kind of like curly braces, so I want code indented inside of that. Now we get to do our translate. We translate to our x and y positions. And then we're going to rotate. And we'll rotate our rotation. So we translate. Oh, I spelled it wrong. No wonder it's red and underlined in black and calling me bad words. It was angry code. So now we translate, we rotate, and now I'm going to redraw my object. And I'll say fill. I'm going to just use my blue again. Now I could have reused the line from above, but easy enough to type that in. Now I'm going to draw my rectangle. And first we'll just put it at 0, 0. Now remember, because we translated to our origin point for the object, then we can start drawing from that origin point. So I'm just going to put it in there. And then I'm going to have a width and a height. And now that we have done this, if I run it, we'll see that I am able to rotate, but I'm rotating around my top left corner. So if I don't want to rotate around the top left corner, but want to rotate either around my middle or around a different edge, then we need to change where are we drawing the artwork. And what I think works well is to draw it so that we adjust the height so we can see where it's rotating around the height, but then I'm going to offset it because I want it to draw around its front. So I'm going to go over by my width. Now, if I make this object no longer square, but if I make it rectangular and draw it, now when I rotate, we'll see, okay. Oh, did I say, I forgot, I need a negative width, not width. Negative width. I need to slide back. Now if we rotate, we'll see it's rotating around its front edge. So now when we rotate around its front edge, and now it's possible to actually keep the object on screen. I hit the down arrow, I can come to a stop. The asteroid screen wrap, we just simply need to modify what we are doing. I'm going to put a comment in here and say asteroid screen wrap, and it's wrap with a W, because we're wrapping a present here. So it really is as straightforward as if x is greater than my width, then x is equal to 0. And now forget a semicolon. And now I repeat that process. If x is less than 0, x is equal to width. If y is greater than height, y is equal to 0. If y is less than 0, y is equal to height. So those 4 lines simply check the 4 borders, and if the player has gone off any one of the borders, it wraps them to the opposite side, or the opposite top or bottom. That's it. So now when I run, I go forward, go off screen. Ooh. We can see it works on the top. Now we'll try the other side. So all 4 directions allow me to perform my asteroids screen wrapping. Now that the screen wrapping is working, it's working in all directions. The player can accelerate, the player can stop, the player can turn. What I think is more fun is to have well, actually the player doesn't accelerate. They go from 0 to maximum speed in one shot. What I would prefer to see happen is that they start accelerating until they hit the maximum speed, and then when you're not pressing the gas pedal, they slow back down and run out of speed. And that's what we're going to work on fitting into it right now. Because right now, if I hit up, I go maximum speed. If I hit down, I come to an immediate jarring stop. Not terribly pretty. So just comment that out. What I would prefer to see happen is say if my speed is less than my maximum speed, at that point, speed will go up by 1. Now, what did I put for max? Okay, max speed is 10, all right. So if my speed is less than my maximum speed, it goes up by 1. So I'm not going to worry about slowing down yet. Remember, the cardinal rule when we're coding is do one thing at a time. If you add in multiple chunks, you won't know what broke it when it breaks. So now if I press, you can see how it speeds up. If I press up once, it goes up a little bit, press again, faster, faster, so I can keep accelerating until I hit my maximum speed. But it's not that satisfying because it doesn't slow back down when I'm no longer pressing the gas pedal. So I'd like to build that it automatically slows down. Now we could say that this is like asteroids, that we have the wrapping going on, I'm speeding up to a maximum speed, and we could do the same thing because if we're in space there's no friction. So we could do the same thing with our, if I press down, what can happen is I can say if my speed is greater than 0, speed minus equal, oh, gotta write out speed, speed minus equal 1. So, and then I need my closing curly brace. Here, so if my speed is greater than 0, make speed go down by 1, but then I'm going to throw in an else, and this is a precautionary measure. Speed is equal to 0. And that's a precautionary measure because if I press down and my speed is greater than 0, so I'm at, let's say, maximum speed, that's 10, it takes away 1, takes away 1, takes away 1. So now when my speed is at 1, I can get down to 0. But if by some weird fluke it landed me at -1 on my speed, -1 is less than 0. So I'm going to now be going backwards when I don't want to. So the speed equals 0 on this else is a precautionary in case by how it cycles input from the keyboard versus running through the draw loop frames, periodically you will get a weird glitch. So now I can speed up and I can slow down by pressing the down key. Now maybe my brakes aren't as strong as my accelerator, so I want to have my slowing down be, say, 0.2 or 0. Well, try 0.5, half as much as it was. Let's see. Maximum speed and then slow down. That's not too bad. So have the brakes. It's kind of like playing asteroids though, where then you have to, kind of, it's our reverse thruster at this point. So maybe you're going to do a space game, not a car game. So it's reverse thruster. That's cool. If we want to have it set up so that we slow down when we are not pushing the gas pedal. What we can do is, if we're not pushing up and if we're not pushing down, that means we're not trying to speed up or slow down intentionally. We'll let friction take over. And to do that, we can say if speed, you may notice a trend here that we're just checking speed. So if my speed is greater than 0, if my speed is greater than 0, at this point we want to slow it down. And we're going to take that speed, and what we can do is, instead of add or subtract, what works well in this instance is we actually use a multiply value, because then we get this kind of incremental where it's more effective. At the beginning it's a more dramatic effect, and then it becomes less and less as we're going slower. It's a less dramatic effect on our overall speed instead of being linear. Linear would be if we're adding or subtracting the same number every time. That creates a linear adjustment. But if we're multiplying it by a number such as 0.95, because if we multiply a number by 1, we get the number. But if we multiply it by a number less than 1, we get a slightly smaller number. But if we say we take 4 and multiply it by 0.95, that's going to take away 5% of 4. But if we take 1 and multiply it by 0.95, that's going to give us 5% of 1, which is now a smaller increment. So what this does is this creates a progressive. The faster you're going, the more it slows you down quickly. But once you're going slow, it's a very gradual tapering off of the speed. So now, if I run this and get up to my maximum speed, you can see how it creeps to a halt. And if you want it to be more dramatic on the slowdown, you make that, say, maybe 0.8. If you do that, you'll find that when you're at maximum speed and let go, you stop very quickly, but better than super abrupt. Now, if you did, say, 0.98, you'll find that it's almost like being on ice, where you're going, and now I let go, and it slowly creeps to a halt. So, utilizing these methods, we are now able to create a more engaging and interesting form of movement on screen. We'll be using a very similar approach with the enemy, but making the enemy chase us is actually going to become a much simpler proposition, and that's what we'll look at in just a moment. To chase our player is it's a very similar process, in some ways slightly less involved. We're going to leave the distance part here because I want it to only chase when we're getting close, but all of the which axis am I chasing on first garbage is going to go away. So with that, hit delete and delete. So now if we remember, we're not using a speed x and a speed y anymore. So those lines will simply just be a speed is equal to 0. Now, this particular thing also means I need to get rid of speed x and speed y and add in my speed 0. But if we look, so we have if distance apart is 300, else my speed will be 0. So that is what we need with that structure, and then we will put where my cursor is right now, this yellow line, that is where we will add all of the actual content to make our enemy start chasing us. But we do need to give our enemy a speed and rotation value. So I'm going to comment out my that and just say float speed comma rotation. Now I'm going to comment out speed x and y there inside my setup constructor, and now speed is equal to 0 and rotation will start at 0. So I will have now my enemy do that. Now the x and y are going to be the same as what was in the sprite, where it's the cosine of my rotation times speed, sine of rotation times speed for y, and then my display is going to be pretty much the same, where I need to use the matrix and translate and all of that. So this is an opportunity where I think copy pasting is probably going to work well. We don't really need to make the enemy wrap the screen because the player never goes off the screen, so the enemy is never really going to go off the screen. So we don't need the wraps, but from the player we can borrow these lines of code the x plus equal cosine rotation times speed, y plus equal sine rotation times speed. So in the sprite, copy that, go to the enemy. I'm going to replace my speed x and speed y lines there with those. So that now takes care of that. And now I just need to worry about the display. Now the display of my enemy is going to be pretty much the same, except I will provide a different, I'm going to use a different fill color so that I can see its enemy. So I go to sprite and copy from push matrix to pop matrix. And I will go into my enemy and I will paste that in, but change it so that my enemy is being filled with the color green. He's green like the nice, rich green color of the flesh of a zombie, or however you want to think about it. Or maybe it's a green leprechaun chasing you, or who knows. Or it's a piece of grass, therefore it's green. It's a little square of sod coming after you because you've been wrecking the environment and the grass is now angry with you. You can figure out what your concept is. At this point, we don't have any, it's not figuring out how to chase, but if I run this, we'll see, okay, it shows up on screen. It's there. Intersection still works, but we need to figure out how to get it to play chase. And getting it to play chase is where we just have to do a little bit more of that scary trigonometry stuff. And what we're going to do is we are going to use the arctangent 2 function. So we will say rotation is going to be equal to a tan 2, arctangent 2. Now arctangent 2, it takes two values. And the two values are going to be y2 minus y1, comma, x2 minus x1. So the way that this works is we're calculating the or the angle between two objects. We want to know what is the angle between two objects on screen. So when I look at this, what is the angle between the player and the enemy? I'm trying to figure out what is that angle, because that's the angle I want my enemy to move on. And what we do is we say, okay, we will take the player's y position, subtract from it the player's, or the enemy's y position. That gives me my first value. The second value is going to be the player's x position minus the enemy's x position. This is one of those weird, rare instances where instead of everything is usually xy, 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 this is now a yx value. That's how the function is written. And you can go dig deeper into the math if you really care. But otherwise, what I am going to say is s dot y, so the sprite's y, we'll subtract from that, not equal, subtract from that the y of the enemy, and then I will say the sprite's x, and subtract from that the x of the enemy. So I'm going to just add an extra set of parentheses. We don't need these, but I think it just makes it a little bit easier to see what's happening. So we have the player's y minus the enemy's y, the player's x minus the enemy's x. So that gives us two numbers that plug into arctangent 2. That gives us a rotation value. Now at this point, what we can do is then say speed is equal to, and give it a speed. Now if we want our enemies to speed up or slow down and have a maximum speed just like the player, we can certainly do that right now. But to begin with, I'm just going to hard code a number in to find out if it works. Again, do one thing, and once it works, add more to it. So this theoretically is going to make the enemy rotate to the player. And then once it rotates to the player, if the player's close enough, it will move in the player's direction. So if I run it, you can see now it rotated to the player. And then I get away and boom. I'm dead. Now if I want it to not be a fixed speed and want it to speed up or speed, have something, we then need a max speed, just like the player had. Why should the enemy be any different? My enemy is sluggish and slow moving. It's a land-born manatee, so it just doesn't go quick. So if my speed is less than my max speed, then I will say speed plus equal 0.2. Now we'll give him a max speed of 3 because it'll take him a long time to get there. Because he's pokey. So I get close and we can see, oh, now he sped up. And we could even set it up so that if it's no longer chasing, it doesn't just have a speed of 0, but it slows itself down just like the player. So we could slow it down just like the player if you are so inclined. So if I am working with the player, instead of speed 0, we're going to modify it. If speed is greater than 0, so as long as I'm not already slowed down at this point, speed times equals 0.95. So instead of killing the speed, we'll make it slow down when it's no longer chasing. And that just makes the whole experience seem more legitimate. Now if you take this knowledge and you combine this knowledge with images instead of crappy rectangles, the whole process becomes a lot more interesting. You go through some pictures in there. Well, we're drawing rectangles. Rectangles are just like drawing sprites. If you're drawing sprites with pictures versus drawing a rectangle, same thing. And that's what you're going to need to figure out how to do.